We're going to focus on the geometry side of linear transformations and see what some examples of them look like when you look at the actual graphs. So we're going to focus on specifically linear transformations in R2 and R3, the plane and the three-dimensional space. In fact, all the examples right here are going to be the two-dimensional versions of them, but you can have similar things in 3 dimensions. And the first thing we'll talk about is reflection here. Now the matrices I'm giving you, these are the standard matrix for the transformation. For example, reflection across the across the x-axis here is x comma negative y, which is the same thing as 1, 0, 0, negative 1 times xy. So what that means is if you have a vector, say this vector here is at 3, 2, and you want to reflect it across the x-axis, it would be the vector 3, negative 2. Now for the next one here, this is reflection across the y-axis. If I wanted to take that same vector 3, 2 and reflect it across the y-axis, it would be negative 3, 2. And that corresponds to this matrix as a linear transformation. And then finally, if I want to switch here, this time I'm reflecting across y equal to x. Now what I mean by that is I need to draw the line y equal to x, and I reflect across it here. This would be the point 2, 3, which is based off of this matrix here. So reflections, whatever type of reflection you're talking about, those are all linear transformations, and you can always find a matrix associated with them to describe the reflection. So basically this is one thing that you're allowed to do with linear transformations. Now there is something called translations. All right, translations, that's where you take a point and then move it further, so you add up two vectors. That's not going to be a linear transformation here. It's not going to satisfy the two properties. You can check that, but translations, they're not going to work for us. Reflections we can, and then these other two things here, we can do either expansion, contraction, or shear. So let me try to explain things here. So expansion, contraction means that if you take a vector, let's say I took the vector 2, 2, and if I then make the x component 3 times longer, but don't change the y component, 1, 2, 3, 4, 5, 6, that would be the vector 6, 2. That would be a horizontal stretch by a factor of 3. However, if I did a vertical stretch, maybe I'll use green for that, vertical stretch here, by a factor of, let's say, 2, I would just stretch in the y direction here twice as far as previous. Now shear, it's a little bit easier to tell what shear are when you look at a whole shape rather than an individual vector. So let's suppose I start out with this rectangle here, and you apply, let's say, a horizontal shear to that. What that means is you're going to shift your x-coordinate out further based on what your y is. So when you're at a point like this, or any of these points, you're not going to shift them right at all because the y value is 0. So that means don't shift it at all. However, as you get higher, you're going to have a y value, you're going to shift it by that much. So in this case, a y by 3, I'm going to shift it right 3 units. So that means this point here is going to go to that. And then what you end up getting is this shape right here. So that's what we're talking about with shearing here. So shearing is kind of stretching it in some way. The idea is you're either going to be changing your x-axis by a multiple of the y value, or changing your y value by a multiple of the x value, whether it's a horizontal or a vertical shear. Regardless, these all here on this page are the main things that you can do in terms of geometry with linear transformations in R2 and R3. There's one other big one that did not make it on here, but we saw it in a previous video, and that is the idea of rotation, which was cosine theta minus sine theta, and cosine theta. And so that was, you take your vector and then you rotate it by an angle of theta there. And these all together make up the things that you're allowed to do, these plus combinations of them, for linear transformations in R2 and R3. And again, you can have R3 versions, you can have reflections in the three-dimensional space, you can have expansions, you can have rotations, all sorts of things like that. The matrices just get a little bit more complicated. And again, I'm not trying to go into huge detail on this video about all these things, just trying to give you a little feeling for what things you're able to do with linear transformations and what things you aren't able to do.